Right, and so in this video we want to return to that idea of the definition of integrability means that double integral over the region for the function must exist. So when does that double integral exist? And so the ideas that we presented in that video was we had to choose a particular point, right? For the Riemann sums, we had in midpoints, point in the lower left, lower right, whatever, right? So we would need to calculate the limit of the Riemann sums over of f over all possible partitions, okay, using all possible test points. Okay, that would be how we could confirm that the function is indeed integrable. Okay. However, there's a nicer theorem rather than so that would be a lot of work. The theorem below gives us a nice way to establish integrability. Okay, so if f is bounded on R, we know what bounded means from Calc 1, but it's been a while since we've talked about bounded, so maybe it's worth remembering. So this is just that there exists little m and big M such that little m is less than or equal to f is less than or equal to big M. Okay, so it has to be bounded on R, and then there's this idea that if the set of discontinuities of f on R or over R have zero area, then we can say that double integral exists, and that's actually really nice. But what is this language about set of discontinuities has zero area? Well, that's where we might need a little assistance. Okay, and so if you imagine for a minute that, okay, you have your little rectangular region, so this is going to be R, okay, and then maybe there's some little grouping of places, okay, so here's our set S, okay, so this one is going to be our set of discontinuities. So, so this is made up of many different places where the function might be discontinuous. Okay, but zero area means that the set S can be covered by rectangles. Okay, so if you can imagine covering this by rectangles. Okay, and the sum of the rectangles, if you were to make those smaller, okay, those rectangles would have zero area. Okay, in other words, that the discontinuities really are just points, are a collection of points and no more. They don't form any sort of geometric shape. Okay, so in other words, if you have an actual area that is discontinuous, that you can find the area of, then you're kind of stuck. Okay, you can't move forward. Okay, so again, this is a nice way to establish that something is integrable. We need bounded. We need that the discontinuities as a set have zero area, so just a collection of isolated points would be great, and then we are given that the double integral exists.